Then in lecture 4, we build the analysis engine. This is the heartbeat of the entire study. We will break down the causality chain, learning how to link a specific cause to a consequence and critically evaluating if your existing safeguards are actually strong enough to stop the accident or not. The causality chain. The core intellectual work of the HAZOP takes place in the analysis of the scenario. A scenario is a narrative chain of events. An initiating cause leads to a deviation which propagates into a consequence unless a safeguard intervenes. This linear logic is the backbone of the study. For example, here we see that a temperature has been changed by an operator manually, and unintentionally he changed the intended parameters which caused increase in pressure. So pressure of the vessel increased, and here we observe that the pressure needle is going towards the red section, and as the pressure increased there is a PSV valve which ruptured and saved the equipment. So here we see that an initiating cause leads to a deviation which propagates into a consequence unless a safeguard intervenes and the system becomes a safe close. Identifying credible causes. A major pitfall in HAZOP is the identification of the non-credible or consequence-based cause. So there is a differentiation between credible cause and non-credible causes. Let's talk about first credible causes. It can be mechanical, instrument, human or external. Mechanically, control valve or diaphragm fail close or open, pump impeller shear, strainer blockage. So all of these are mechanical causes. Instrument, transmitter drift, false reading, frozen signal. So all of these are instrumental errors. Human cause, operators enter the wrong set point, valve left manual, bypass left open after maintenance. So all of these are human causes. External causes could be power dip, cooling water, header failure, instrument air pressure loss. So all of these are external problems. What if we talk about non-credible causes? It can be something like pipe leak. Unless there is a specific corrosion mechanism, random pipe failure is usually considered a consequence of overpressure, not a root cause. Unmitigated consequences. If there are some parameters which have been left unnoticed during HAZOP analysis, so what can worst happen? To accurately assess risk, the team must evaluate the consequence assuming all active safeguard fail. This unmitigated risk represents the worst case potential of the system. Let's take an example of cooling water pump failure consequence. There are two examples where a pump coming from cooling water has been failed that is used to cool down the reactor. So in first case, if the reactor fails, the temperature or pressure of the reactor will rise up, high temperature alarm sounds and the operator trips the reactor. In this way, the reactor will shut down safely and it will cause economic loss only. But on the other hand, if a pump fails and reactor runaway conditions happens, so it will cause a rupture, and with the rupture there will be toxic gases cloud release. Potential fatalities can be occurred with this problem. So if we compare the mitigated consequences or safeguard, so the high temperature alarm sounds, the operator trips the reactor, economic loss only. But for unmitigated consequence, the reactor runs away, pressure exceeds vessel rating, vessel ruptures, toxic gas cloud release, potential fatalities. The HAZOP must record the unmitigated consequences to determine if the existing safeguards are strong enough or not. If we only look at the mitigated outcome, we might falsely conclude that a simple alarm is sufficient protection for a fatal hazard. Now let us talk about the hierarchy of safeguards. Actually, these safeguards act as barriers to the progression of the incident. In HAZOP, we prioritize them based on the hierarchy of control. So there are 6 ranks of hierarchy of controls. Number 1 is inherently safe design. The vessel is rated for the maximum possible pressure, full vacuum to 100 bar. No active device is needed. Number 2 is passive device. Mechanical barrier like dike walls, blast walls or restriction orifice. In this way, we provide boundary to the problematic area. Number 3 is active hardware. Pressure safety valves, ruptured discs, these are highly reliable but can fail. Number 4, safety instrumentation system SIS. Automated trips, interlocks, that act without human intervention. Number 5 is active human intervention. Alarms. These are valid only if the operator has sufficient time, typical less than 10 to 15 minutes, and means to respond. Administrative. Procedures, training, signs. These are the least reliable and should rarely be the primary safeguard for high consequence hazards. The HAZOP worksheet is just a list form of the Bowtie. Causes are on the left, consequences are on the right, and safeguards are the barriers we erect to stop the timeline from progressive to disaster. Now look at these stages one by one. Stage 1, deviation, high pressure happens, which cause a regulator failure. So this regulator failure can result into a rupture, but if we are providing some prevention barrier, for example maintenance time by time, this problem can be stopped. So for example, high pressure can be a reason because of regulator failure or thermal expansion, which can be stopped by a maintenance or thermal expansion by control loop. Both of these causes can result into some consequences, for example rupture and fire. For rupture, we have a stage 5 mitigation barrier, for example PSP applied, or a mitigation barrier, fire sprinklers have been installed with the fire catching area. So in this way we can see that a list of HAZOP consequences or sequences can be converted into a Bowtie diagram. Now there are two questions, you can answer them in comment section, or you can see these questions for your interview or vivas. Why is it necessary to record an unmitigated consequence rather than the expected outcome? Question number 2. Under what conditions is an alarm considered a valid safeguard in HAZOP? So you can reply this question with chapter numbers in comment section. Common guide words interpretations by equipment. So there are names of equipment, general equipment that are used in nearly all industries. For example, centrifugal pump, no flow, it shows tripping, suction valve closed or strainer plugged, or it can show a more pressure, discharge blockage, deadhead has been created, or reverse rotation. It can also show a high temperature. This also represent a deadhead or bearing failure. For heat exchanger, no flow means tube blockage, falling inlet valve closed. More pressure means tube rupture, high to low pressure side. High temperature means cooling water failure, falling bypass open. For a vessel or tank, no flow means outlet blockade, pump trip. More pressure means vent blocked, gas blow by or fire. Or high temperature means external fire, chemical reaction or heater failure. For control valve, fails closed, air failure, diaphragm tear. More pressure means fails open, if upstream pressure is high, bypass open. High temperature means not applicable directly to valve but to a system. So here we see some equipment name and we applied some guide words and we have seen their consequences that can occur with the change in variation of the guide words. Further, HAZOP is an indispensable tool for identifying process hazard, but it is not a completely risk assessment strategy on its own. It is best viewed as a powerful hazard identification filter that needs to be supplemented with other tools like quantitative analysis and component level studies to build a complete safety picture.